In the fiscal year 2026 operational environment, the B-1B Lancer has completed its transformation from a Cold War penetrator into the United States Air Force's most potent airborne anti-ship missile truck. The aircraft carries 24 AGM-158C LRASM weapons internally across 3 rotary launchers. And with the Load-Adaptable Modular Pylon program now funded and progressing, external carriage will add an additional 12 missiles on 6 wing stations, bringing the theoretical maximum per-sortie payload to 36 autonomous sea-skimming threats. It must be noted, however, that a full 36-missile loadout imposes severe aerodynamic drag and fuel consumption penalties, reducing both combat radius and maneuverability to a degree that makes the B-1B more vulnerable to long-range interception by land-based J-20 fighters. Operational planners must therefore balance salvo weight against aircraft survivability, and the realistic combat configuration may remain closer to 24 internal weapons for deep penetration missions. The B-1B launches these weapons from a standoff distance that places it safely outside the engagement envelope of any surface-to-air missile currently deployed aboard Chinese escort vessels. Its approach profile relies on low-altitude flight and mission planning that exploits radar shadowing from island terrain where available. But the aircraft is not stealthy in the modern sense. Its radar cross-section is measured in square meters, not the fractions typical of true low-observable platforms. And its flight path from known bases in Guam or Australia is operationally predictable. The B-1B compensates for this vulnerability entirely through the range of its payload, the volume of its salvo, and the ability to coordinate with electronic warfare escort and satellite-based targeting. The platform is not designed to survive inside contested airspace. It is designed to never enter it. The AGM-158C LRASM is best understood as an autonomous targeting system that uses a missile airframe for delivery. Its baseline AGM-158C-1 variant, derived from the JASSM-ER, achieves a range of approximately 926 kilometers, while the C-3 extended range variant, currently in early operational capability, pushes that figure past 1,000 kilometers under optimal flight profiles. The LRASM's cruising at high subsonic speed, Mach 0.8 to Mach 0.9, meaning a maximum range shot requires roughly 55 to 60 minutes of flight time from launch to impact. While this extended flight duration is frequently cited as the missile's most significant tactical weakness, the subsonic profile confers an underappreciated advantage: thermal stealth. Supersonic and hypersonic missiles generate enormous aerodynamic heating due to skin friction, making them highly visible to electro-optical and thermal sensors deployed aboard Chinese destroyers. The LRASM's relatively cool subsonic skin temperature significantly reduces its infrared signature, complicating detection by electro-optical and thermal sensors, particularly in the cluttered maritime environment. The missile's multi-mode seeker architecture combines GPS and inertial navigation, a passive radio frequency sensor that homes on shipboard emissions, and an imaging infrared terminal seeker with onboard artificial intelligence capable of autonomous target recognition and path planning. The 454-kilogram semi-penetrating blast fragmentation warhead is optimized to disable large surface combatants through mission kill rather than outright sinking. The LRASM's low absorbance shaping reduces its radar cross-section substantially, particularly against X-band fire control radars, though it remains more detectable to lower-frequency UHF and VHF systems that China has deployed extensively. The missile's data link enables cooperative behavior among multiple weapons in flight, allowing a salvo to share sensor information, deconflict targeting assignments, and coordinate simultaneous impact timing from divergent approach bearings. China's ability to detect an incoming LRASM salvo depends on a layered sensor network that begins with land-based early warning systems and extends to carrier-based airborne platforms. The KJ-500 airborne early warning and control aircraft, with an endurance of 12 hours and a combat radius exceeding 5,000 kilometers, provides persistent coverage from mainland bases. Its AESA radar is officially credited with a detection range of 470 kilometers against fighter-sized targets, but against a low-observance cruise missile with a small radar cross-section and a sea-skimming terminal profile, effective detection range compresses to an estimated 150 to 200 kilometers under realistic operational conditions. The KJ-600, China's new carrier-based AEW platform, comparable in concept to the E-2D Hawkeye, operates directly from the Type 003 Fujian and provides the critical over-the-horizon radar coverage that surface ships cannot achieve due to the 40-kilometer radar horizon limitation against low-flying threats. Radar analysts assess the KJ-600's effective detection range against a target the size of an LRASM at approximately 270 kilometers. Complementing these airborne sensors are ground-based anti-stealth radars such as the JY-26 and YLC-8B, which operate in UHF and VHF bands less affected by the shaping techniques that reduce X-band radar returns. These systems can detect low-observant targets at ranges up to 500 kilometers under ideal conditions, though their angular resolution is insufficient to generate weapon-quality fire control tracks independently. The integration of data from these disparate sensors through a unified command network is designed to create a composite track of sufficient fidelity to cue fighters and surface-to-air missile systems before the LRASM descends below the surface radar horizon. Once a credible track on an inbound LRASM package is established, the first layer of active defense falls to the carrier's embarked fighter force. The Type 003 Fujian Air Wing comprises approximately 50 to 60 aircraft, including 12 to 24 J-35 stealth multi-role fighters and 24 to 36 J-15T heavy fighters. In a combat surge scenario, roughly 60 to 70% of this force is available for immediate tasking, translating to 20 to 30 fighters on combat air patrol or ready alert status. The J-35 carries the PL-15 Beyond Visual Range air-to-air missile internally, with a published range exceeding 200 kilometers, while the J-15 can employ the same weapon from external hardpoints. The engagement concept relies heavily on the KJ-600 operating as a quarterback, transmitting track data via secure data link to fighters that can then launch missiles without activating their own radars, preserving the element of surprise and reducing the threat's warning time. The PL-15's dual-pulse rocket motor and ESA seeker provide a credible capability against a maneuvering subsonic target, though the engagement geometry against a sea-skimming cruise missile is more demanding than against a fighter at altitude. The time available for interception is constrained by the LRASM's flight duration. A missile launched from 900 kilometers requires approximately 55 minutes to reach the target, and after the initial detection and track establishment phase, the fighter force has perhaps 20 to 30 minutes to conduct multiple intercept attempts before the missiles enter the inner defensive layers. The Chinese carrier strike group's surface combatants form a layered defensive architecture that begins with the Type 055 Renhai class destroyer. Each Type 055 displaces 13,000 tons and carries 112 Universal Vertical Launch System cells, while the accompanying Type 052D destroyers contribute an additional 64 cells per hull. A typical CSG escort package of 1 or 2 Type 055s and 2 or 3 Type 052Ds provides a total of 300 to 450 VLS cells across the formation. Chinese naval doctrine places extraordinary emphasis on fleet air defense, and operational analysis suggests that a significantly higher proportion of VLS cells, perhaps exceeding 70%, is allocated to surface-to-air missiles during high-threat transits. This includes not only the long-range HHQ-9B, but also the medium-range HHQ-16 carried aboard Type 054A/B frigates escorting the formation. Consequently, the total number of air defense interceptors available to a Fujian-centered CSG may approach 250 to 300 rounds, substantially more than the conservative 150 to 200 estimate. The remaining cells are occupied by YJ-18 anti-ship cruise missiles, anti-submarine rockets, and a smaller number of land attack weapons, reflecting the CSG's primary mission of sea control and fleet defense rather than power projection ashore. The fundamental asymmetry in this engagement is temporal. The LRASM's subsonic cruise speed of approximately Mach 0.85 gives the defending force a window of roughly 1 hour between launch and impact when the missiles are fired from maximum range. This time is both an advantage for the defense and a constraint on its ability to sequence engagements effectively. The kill chain from initial detection to interceptor launch involves multiple sequential steps. A KJ-600 or KJ-500 radar detects an ambiguous low observable contact at extended range. The track is correlated with other sensor data to confirm it is not a false return. The Combat Information Center evaluates the threat priority among potentially dozens of simultaneous contacts. The fire control system computes an engagement solution, and the launch authorization is transmitted to a VLS cell. Under peacetime conditions with a fully alert crew, this process requires approximately 60 to 90 seconds. Under combat stress, with electronic warfare jamming, degrading sensor fidelity, and multiple tracks saturating the display consoles, the timeline extends to 3 or 4 minutes per engagement sequence. Against a single missile, this delay is manageable. Against a coordinated salvo of 24 to 36 missiles arriving on converging bearings, the cumulative time required to process and engage each threat sequentially exceeds the available flight time of the later missiles in the salvo. The defense is not necessarily defeated by any single technical failure, but by the arithmetic of engagement capacity versus threat volume. The most consequential vulnerability in the Chinese CSG defensive architecture is not sensor performance or interceptor kinematics, it is the finite depth of the missile magazine. A strike package consisting of 2 B-1Bs launching a combined total of 48 to 72 LRASMs presents a salvo size that approaches or exceeds the total number of HQ-9B interceptors carried aboard the escort formation. Even under optimal conditions, where every interceptor successfully engages and destroys its target, the CSG faces magazine exhaustion before the entire salvo is defeated. In practice, intercept probability against a maneuvering, low observable target is substantially below unity, and the defense must allocate multiple interceptors to high-confidence kills against the most threatening tracks. This dynamic is compounded by the LRASM's autonomous targeting logic, which prioritizes high-value units and adjusts terminal approach vectors to exploit gaps in defensive coverage. The coordination among missiles in flight further complicates the defender's fire control problem, as the salvo presents as a distributed, multi-axis threat rather than a single stream from one bearing. The cost-exchange ratio is also instructive. An LRASM unit cost of $3 to $4 million against an HQ-9B interceptor cost of $1 to $2 million appears favorable to the defense in isolation, but this calculus shifts dramatically if even a single missile penetrates the screen and achieves a mission kill on a Type 055 destroyer valued at over $1 billion or forces the carrier to withdraw from the operational area. The analytical community converges on a range of plausible outcomes that avoid the extremes of either total penetration or complete interception. In a scenario where the United States achieves tactical surprise, coordinates electronic warfare support from EA-18G Growlers, and launches a saturation salvo from multiple B-1Bs on divergent bearings, a penetration rate of 10 to 20% is a defensible planning assumption. Crucially, the presence or absence of robust electronic warfare support represents the single most significant variable in this equation. If EA-18G Growlers and the B-1B's own electronic warfare systems successfully degrade the KJ-600's radar fidelity and disrupt the Type 055's fire control data links, the penetration rate could climb toward 30 or even 40%. Conversely, if Chinese electronic countermeasures neutralize the jamming effort and the defensive sensors operate at full capability, the penetration rate may collapse to single digits. This translates to 3 to 7 missiles, or potentially significantly more, reaching the inner defensive layer, and perhaps 1 to 3 striking the carrier or its escorts. A hit on the flight deck with a 454 kilograms semi-penetrating warhead disables aviation operations for days to weeks without necessarily threatening the ship's buoyancy. The carrier is forced to withdraw, and the strike group's offensive capability is neutralized for the duration of the repair cycle. In a scenario where Chinese early warning functions optimally, with persistent KJ-600 coverage, effective integration of land-based anti-stealth radar tracks, and well-timed fighter interceptions, the penetration rate falls below 5%. Most missiles are destroyed before they enter the inner defensive ring, though 1 or 2 may still leak through to strike an escort vessel. The carrier remains operational but has consumed a substantial fraction of its defensive interceptor inventory, rendering it vulnerable to follow-on strikes. In neither extreme is the carrier sunk, and in neither extreme does the B-1B force operate without risk of detection and counter-air engagement from land-based J-20 fighters armed with PL-17 ultra-long-range missiles. The strategic reality is that both sides possess credible capabilities that make this engagement prohibitively costly to attempt except under the most extreme political circumstances. The existence of the capability is itself the deterrence, and the threshold for its use remains the defining variable that no technical analysis can resolve.